Welcome, viewers, to the third episode of ScienceOverse Expert Panel, where we bring experts from different scientific fields. And I'm your host, Anirban, the coordinator of Astronomy Department of ScienceOverse. And today we have with us a wonderful host, Ma'am Funmilola, Dr. Funmilola, and she is an astrobiologist, and currently she is the Assistant Chief Scientific Officer of the Space Agency of Nigeria. Welcome, ma'am. Welcome to the podcast. We are very lucky to have you here.
Yeah,
And
thank you very much.
let's begin the podcast. Ma'am, can you please introduce yourself to the viewers?
Okay. First and foremost, let me say thank you for having me. So once again, I'm Dr. Funmilola Oluwafemi, and I'm an astrobiologist. I'm a space life scientist and an extreme environment researcher. I actually have the background of biochemistry, and I work with the Nigerian Space Agency at the Space Life Sciences Division, and I research using the microgravity platform on several samples. Yeah, for sure, it's
Okay.
for now.
Yeah. So see, we have an interesting guest with us. You do astrobiology, right? You have done your research on astrobiology, if I'm not wrong.
Yes, I research around astrobiology. I'm an astrobiologist. Yes.
Okay. So yeah, this department of science of us that is you know the science of us who have arranged this meeting, and this department is also regarding astrobiology and astronomy. So the department is known as science of us, astrobiology and astronomy department. So yeah, we do have some astrobiologists here too, and we will be glad to ask you questions about astrobiology. So yeah, I think we should proceed with our questions. So, ma'am, can
Yeah.
you
Okay.
elaborate a bit with your what you do actually, your work or your research area, the particular your particular research topics, like how you're impacting the world.
Hmm. Okay. So, as an astrobiologist, there are actually there is going to be a platform, to access the space environment before this work can actually be done. So, in the search of the space environment, there are actually several platforms of microgravity environments, because space environments has two specific characteristics, which are radiation and microgravity. So to have the space environments in the first place, there is need to be able to access microgravity platform, and there are different avenues or different microgravity platforms. We have the real microgravity platforms, that's orbital, and there's also suborbital. They're actually real microgravity platform. For the orbital, going to the space station, like International Space Station, and that. And then for this suborbital, like using sounding rockets, and then using some um aeroplane as well. You can also access real microgravity platform from there. And then from there, we now go to the ground-based microgravity platform, which we have the analog and the simulated microgravity platform. For the analog, it has limitation, and the research that can actually be conducted under that platform majorly cardiovascular, that needs to deal with, maybe like circulatory system. So that has that limitation because it is analog. While for the simulated microgravity environments, it also has some advantages and some disadvantages, So that platform actually mimic microgravity environments. And but from that simulated microgravity platforms, we are able to have long access to microgravity. Hence, plant research is possible with that. So many experiments that can take hours, can be conducted under that platform. While for the other platforms, that's for like the like the drop tower, it can only grant few seconds of microgravity, and then it is mostly physical sciences experiments that can be conducted under that platform. So this is just by the way, this is giving a general introduction. So having the microgravity environment, at one's disposal, in quotes, can make someone to be able to perform astrobiology experiments.
So, ma'am, you mentioned that we do create microgravity environments while being here on Earth, like using drop platforms or that aeroplane that moves through that parabolic path, right?
Yes,
Yeah.
yes,
So
exactly.
it's pretty interesting how we can achieve such things on while being here on Earth. So, can you please explain what kind of challenges do you face while doing these microgravity experiments? And especially because we are in presence of Earth's gravity, it's massive gravity of Earth. So what challenges do you face, and what kind of workarounds do you have to go through to mitigate this challenge?
Okay, okay. So actually, the major challenge, is being able to access the real microgravity environments, because um, um, the simulated microgravity environment, I told you, it has limitation, and the limitation is that it's not give 100% results compared to the real microgravity environment. It is not going to give 100%, although it can give something close or something very close, but not 100%. And for the analog microgravity platforms as well, I said it is majorly for cardiovascular experiments, while other experiments will not give good results. So accessing the real microgravity environments is the greatest challenge. For the suborbiter as well, it grants access for only few seconds microgravity, of which some experiments, takes hours. The experimenter actually wants to put the sample under microgravity environments for hours, but suborbiter, is not going to give this access. But for the um, space laboratory, it is 24 hours, So, but accessing it is a scarce environment, is rare, and it's expensive to actually
Yeah.
access. Yeah, so that is actually the greatest challenge. But however, these other platforms, they are actually contributing to a great extent, to microgravity research, And another challenge is also getting an equipment to also simulate microgravity environments. So these are the challenges that actually surround this particular research.
Okay. So, for our viewers, they might not be familiar with the particular physics involved with how we create microgravity on Earth. So, as far as I know, it's briefly about that. It's related to that Einstein's, you know, what he called his happiest thought of his life, that if you undergo free fall, the gravity seems to disappear for you. So can you please briefly explain the physics behind microgravity and how we create it in while being present here on
Okay,
Earth?
so yeah, so on the normal heights, gravity, in the whole world, gravity exists. And even when we are talking about microgravity, the micro is still there. The micro is still attached to the gravity. So the gravity is still there. The gravity can never leave. So in some cases, there are some people that record that they did experiments under zero gravity environment. It's not possible. It's not actually possible. So it is actually microgravity, because there is no way you can eliminate all the gravity. It's not possible. So it's microgravity. So on the Earth, there are, as I mentioned, there are some real platforms that are still found on the Earth, and this involves the drop tower, the sounding rockets, the balloon as well. Give access to this real microgravity environment. But there are advantages and disadvantages. For example, if you actually want to use balloon for your experiment, the experimental setup, it is inside the balloon and it is being taken up there. So recovering it, everything needs to be planned. Everything needs to be planned. So recording, that's retrieving. That experiment part needs to be planned. Then for the drop tower, there is actually one in Bremen, Germany, and then it is as well, a little difficult, or it is not so accessible unless you apply, and then your experimental procedure is acceptable by them and the whole, and it is approved, and then you need sponsor to actually do that. Sir, United Nations Office for Outer Space Affairs actually put that up in conjunction with that platform, whereby people apply and then they are able to access that platform for their microgravity experiments. And as I mentioned before, it also gives just few seconds, like I think 8 seconds, depending on the kind of throw you are using, or 12 seconds. So which some experimental samples require more time. It is only physical sciences experiment that can be conducted within that short time. But for life sciences experiments, I'm talking about life, talking about plants, animals, before they can be able to respond. For example, plants, to grow plants, to even germinate a plant, some of them if it's very fast, it will take 2 days or 3 days. There are some that won't germinate like 7 days or even more. So that means you need that long time frame to be able to conduct life sciences experiment. So for simulations, there's microgravity simulation platforms. We have clinostats. We can use the clinostat. We have random positioning machine, and then we have magnetic levitator, that can also be used, and others. as well that can be used for microorganisms experiments as well on that simulated microgravity platform. So they are actually accessible. Simulated microgravity environments are more accessible than the real microgravity environments, like the orbiter and the suborbiter. And they also give longer time frame for the experiments.
I see. So the main challenges, as I hear from you, is that in the simulated microgravity environments, what they do is they make a sample free fall, and that creates a kind of microgravity environment inside of the
Exactly.
sample. But the problem is that
Exactly.
that environment is only maintained for a few seconds because that thing is falling
Exactly.
down. But most
Exactly.
biological processes need more time than a few seconds. That's the main problem with the
Exactly.
simulated microgravity environment, right? Okay.
Yeah.
So let's shift our discussion from microgravity to more general stuff like, or I would say another interesting astrobiology topic. Uh, since
Okay.
the first day I started learning about all these things, the first thing I learned was habitable zones. Like, what is a habitable zone? It's a zone around the star where kind of it's feasible for life. So
Mm.
I know over the years that definition has changed a lot, and it's I think it's not mandatory for us planet to be at a specific distance. I think now they are talking about that life can also be found near the moons of certain planets. So my next question to you would be, how do you define a habitable zone in the context of exoplanet exploration, or what criteria do you consider when searching for extraterrestrial life or habitable zones around stars?
Okay. So, um, habitable zones, before now, before now, I'm sure we avoid as kids. We watched some films that they were telling us there are aliens in some other planets, that you feel that some people, probably having horns and all that living on other planets, So it was always an interesting stuff then. But now research has gone beyond that. We now know that there is no other planets, that has life except the Earth. Yes, how was that deduced? It was actually deduced by sending rovers or robots, which can be named rovers and some other names that are given to them, is sent onto those planets, and then on them have been attached cameras, and then you are able to see what is going on those planets. There are so many people, they find it confusing. They will say, we have been seeing pictures from Mars. It means people have been there. And then I'll tell them, no, nobody has gone to Mars. I said, well, we see the pictures of this. I say, yes, you see the pictures because there has been robots that has been sent there with them attached cameras, and then you're able to see the pictures. So science has actually gone that far for us to see the pictures of those planets and for us to know that there is no life that is existing except on the Earth. Yeah. But out of the planets, you know, the ones that is closely having the characteristics of the Earth that can make life to exist is Mars. That is why it has been several research going on about exploration of the Mars, for life to exist there. There may be so many challenges that may come in the future that may, just wipe the whole earth away. But by the time we have spread to the next planet, life will still actually continue. So from those experiments or research that have been conducted in the past, we know there is no existence of life anyway, except for microorganisms that were detected, on Mars. Yes, so there is no existence of life anywhere except on the Earth currently, and there are actually so many characteristics of such planets that makes life to exist. On Earth, we have oxygen. We have sufficient oxygen that can support life. In those in the other planets, there is no sufficient oxygen. They are just minute, which is not sufficient to support life. That is for human, and for plants as well. For example, plants, there are so many things that plants needs, from the soil. For example, the plant needs nutrients from the soil. And for example, on Mars, there are regoliths. There is no good soil that can support the plant to live. So the environments of the other planets and every other celestial bodies on in the universe, does not actually support life. And there is no existence of life anyway, except where we go and make life to happen.
So basically, you were saying that we haven't found life yet in our vicinity of the solar system. So do you believe this, that we might find life elsewhere in some exoplanet, even if we cannot contact it or as such, but we may detect life on other planets, other exoplanets, planets that are not part of our solar system? Do you think that this is a possibility in future, that some other planet?
Okay, we can actually wait till then. We may wait till we find out, but these are the surrounding keynotes about that. Most of those exoplanets, they don't have the characteristics, of life supports. They don't have those characteristics. Once there is no oxygen, for human, there cannot be life. There cannot be life. It is not possible. And then most of them as well, they don't have liquid water. And how can life exist without water? Like on the Mars, there is no liquid water. It is only ice. It is only ice. So there are so many things that are actually surrounding the existence of life. So I don't want to frankly say there will not be, that we cannot get life. Let us wait till then when we get life. But with their characteristics, it is not likely.
So would you agree with the statement that although other exoplanets, they don't have conditions like what we have here on Earth, so those planets are unsuitable for human-like life forms or plant-like life forms. But what about the life forms that are, frankly, like alien to us, like chemotrophic life forms who survive on chemicals, like at the bottom of the ocean or something like that? So, is there a possibility that we may find some kind of microorganism life, like micro life, not life like us or like plants? like chemotrophic microorganisms who exist on other exoplanets and feed off the chemicals of that planet. Uh, do you think that this is a possibility? Like very basic
Okay.
life form?
For microorganisms, it is still possible. It is possible for microorganisms because we have some extremophiles, even
Yeah.
on the head here, at the extreme regions and environments, we get some extremophiles there. So if it's for microorganisms, there is possibility. There is the possibility because
Okay.
they may, be able to survive under such extreme conditions.
Yeah. So based on this discussion, we see that the that definition of habitability, like the habitable zone of around a star, that does not strictly include that yeah, life, human-like life forms have to be there to call the planet a habitable planet. But there
Yeah.
can be other kind of life forms that are there. So based on these considerations, can you tell me that how would you define a habitable zone? Like, what are the criteria that a planet need to fulfill to call it that yeah, this planet lives in the habitable zone of that star?
Okay. So from my personal judgments, from my personal judgments, that there has to be existence of oxygen. Oxygen, that is majorly for man, has to be existence of oxygen. Even if it's not as much as on the head, there has to be some sufficient amounts that will be able to be available. And then I will as well say existence of reduced gravity, which is what we have on those planets, on those planets. Yes, reduced gravity, not microgravity, because by the time there is transportation from the Earth to another planet, you have passed through all along through the microgravity zone, and then by the time you are getting to another planet, it is reduced gravity. So of course, so there is reduced gravity, and then there should be water. There should be water. If liquid water can be generated, like the research that is actually going on for Mars exploration, there has been deduced a way of getting liquid water, like dissolving the ice actually, but it still needs to be purified, and then platform to be able to mimic gravity, because it is microgravity that it is reduced gravity that will be accessible just naturally. So, like simulating gravity, being able to simulate gravity so that the body physiology can be maintained. So those are actually key. Those are actually key. And then there should be a way to be able to shield from radiation, to be able to shield from such radiation. And one of the ways that has been deduced, that is also proposed for Mars exploration, is burying the habitats. That by the time the habitats are buried, there will be minimal radiation, deadly radiation that will get to the explorers. So I think those are the four major from my hand.
Okay. Okay. So yeah. like if we are talking about planets that you know by life, I'm talking about planets that have naturally, given rise to their own form of their own life forms. So by the standards that you have discussed, that yeah, it's important that the planet must have some kind of source of liquid water. It has to be shielded from radiation so that those life forms can thrive in that planet if they naturally arise there. And yeah, so to me, the definition of a habitable zone would be a planet residing in such an area that has the supply of liquid water, that has you know the required amount of oxygen or other elements that are necessary for life, and the planet has some kind of atmosphere that shields the habitable environments from
Um,
the harmful radiation of the
radiation,
star or the space, right?
radiation, yes. Yes,
Okay. So coming, since we're
yes.
already talking about life forms arising on exoplanets, if if an exoplanet, suppose in a hypothetical situation that there is an exoplanet that has given rise to life naturally, so it has its own microbiome, it has its own biosphere, and we are detecting that planet from here using our telescopes. We have like we have methods to uh, see exoplanets and analyze their atmospheres and see what kind of chemical signatures the atmosphere of those exoplanets have. So,
Mm.
what specific chemicals do you think signify that, yeah, this planet might be habitable? Like, what specific chemical signatures or biosignatures are there that would indicate if such a planet exists? What kind of biosignatures would indicate that, yeah, life exists, probably exists in this planet?
Okay, yeah, there are actually several experiments that can be conducted to know if probably life exists, especially um you know microbiology experiments. You know, I'm actually a biochemist. I am actually a biochemist, but I know there are specific experiments, that can be conducted to know if a particular microorganism exists in a particular arena or not. So I won't be able to speak more on that
Okay.
question.
So
Yes.
I will ask a question related to that. So suppose we have studied a lot about our own Earth and how it was like a few billion years ago when life arose on this planet. So based on that knowledge, what do you think uh, would lead us there? Like, if we find a planet and we do the analysis on the atmosphere of that exoplanet, and we find certain chemicals, and are there any chemicals that would tell us that, yeah, this chemical is a product of probably some kind of life form on this planet? Are there any such chemicals that exist?
Yeah, I believe there are chemicals as such. As I mentioned before, it has been deduced that there are existence of of microorganisms on Mars. Yes. I'm sure there are specific chemicals that are actually probably produced by one microorganism or the other that will be able to let us know that.
Okay. So it's a
Yeah.
good thing that we have like telescopes like James Webb around to you know tell us about the atmospheric compositions of different planets. And
Exactly.
how much hope do you have that we might detect a planet that contains its own life forms, like be it micro or macro, be it on the micro scale or the macro scale? How much hope do you have that this discovery would be made within our lifetime?
Wow. So we must be optimistic all the time. We must be optimistic all the time, you know. For example, you know, every decade, every decade since is in 1960 thereabouts, it is always saying the coming decade we are going to explore, you know, we are going to send man to Mars. From 90s, like around 1960, it has been said the next decade. After getting to that next decade, they say the next decade, the next decade. And even up to now, we are still saying the next decade, you know. So, but it is actually doable. You know, it is actually doable. We can um man can survive, you know, in those other planets like Mars and even Venus as well. After Mars, it says Venus, you know, that is being bid for as well. That man can live in the cloud of Venus. You know, it is. I'm not going to say it is not possible. It is possible because even space technology in the first place, you know, it is science. It is believing that this thing can work, and we have so many benefit from it. Even how we are talking virtually, it is actually benefits of space technology. So it is actually possible. There is nothing impossible. We can explore those planets, and life can survive, even man, not just microorganisms or small lives, but humans can actually
Okay.
survive on them.
Yeah, Mike, you answered the question that how much hope do you have about man exploring other planets, other exoplanets? But actually, my question was about how much hope do you have to detect a planet? We don't have to go there, just detect, make a detection
Okay,
that yeah, this planet might have some kind of a life form. So, do you think
okay.
that this discovery would be made within our lifetime? Like a
Yeah,
planet, exoplanet that harbors some kind of life form?
yes, it is. It is possible.
It is
It
possible,
is.
but yeah, we will have to
Yeah.
manage our expectations. So,
Yes,
so since we are already in our astrobiology domain, so one last thing that I would like to ask you from astrobiology is that how do you think the field of astrobiology is going to impact the future space explorations?
okay. Yeah, there are actually diverse ways, you know, that it is going to impact, you know. So existence of a life on other planets, you know, needs to start with some certain research, of which certain result has been gotten. So it is not until those people get to such planets before they will start finding solutions to those challenges that were already there. So the astrobiology research, you know, it has already um, it is helping to do certain to carry out several researches, you know, that is useful for those explorers, whereby solutions will have been deduced for those challenges that they are going to meet there at the end of the day. So it is quite important.
Yes, and even today we see that NASA is also putting tremendous amount of work in trying to solve some potential problems related to this field of astrobiology and space exploration. One of the main things that we see NASA is doing, and I kind of like it, that they are extending their hands towards citizens and you know students. Like they conduct a good hackathon called NASA's uh, something called I think NASA SpaceX Challenge. So what they do is that they ask students to come up with solutions to problems that
Yeah.
NASA is currently facing in the field of astrophysics or astrobiology or astronomy or planetary science. So yeah, this is kind of a fun initiative that I see that certain space organizations that they take. They try to solve these problems from using, the collective intelligence of students and researchers and other people. So what do you think do you think these kind of citizen science programs, they are, there will be a big step towards achieving these goals in towards you know humanity's progress in space?
Yes, they actually good programs and a good platform, to expand knowledge and to also have results towards those explorations. For example, those competitions that are being brought up for students, it is making them to develop interest as well in that field of research. It is training them, it is catching them young into such sector. It is catching them young. And those challenges that has been since maybe 1960 that we're not able to have gotten beyond, Earth and Moon, that has not gotten us to Mars, you know, can be deduced. The solutions can be deduced from them. And I also remember India as well, performed that experiment for plants and the others for that ecosystem to exist. And that is also a very good one. Such platforms are actually great platforms to explore those planets. They are good.
Okay, look, moving forward to our next set of questions. Uh, how do you think we should approach the issue of planetary protection? Like when we land a rover, like you were talking about the landing rovers on Mars, uh, there is a slight chance that we may contaminate that planet with the microbes of our own planet, like some kind of a bacteria that rides with the payload and contaminates Mars. And if we these most of these bacteria are extremophiles, and suppose they survive on Mars, they actually they're so let us imagine a situation that we send a spacecraft to Mars to for some different reason, for some kind of scientific research, and that spacecraft has some earth bacteria in it as contamination. And when that spacecraft reaches Mars, that bacteria somehow survives on that planet. And later we discover that bacteria using our other space programs that are designed to detect life forms on Mars. So it's a kind of a contamination. We would detect that bacteria, but it's actually not Mars bacteria, but Earth bacteria. So what do we do, or what are we doing to prevent such kind of contaminations in planetary exploration?
Okay. So actually, as you have mentioned when you were speaking, initially there were no microorganisms in space, except as we have discussed before that it was detected that microorganism existed, but was no more in existence. So no existence of microorganisms in space, except for the ones that are being taken along, so to say. But there are actually several screening system that has been put in place, or that are in place for those that will be traveling, to the outer space. They are always being screened. That's number one. They're always being screened and isolated several days, even before they are allowed to make such travel. But aside that, even after being screened and then they deduce, okay, you don't have any microorganism, on you that you are taking along, there are certain experiments that are going to be performed, on the space flight. So some of these experiments as well generate microorganisms, like experimenting with the plants, with animals and the others. They are going to grow some certain microorganisms. So that there should be some particular system that will have been put in place. Everything should have been calculated, and then there should be restriction. There should be restriction around those microorganisms that may be generated during such experiment. So the same also goes for unmanned missions, like sending those rovers. They should make sure they're actually very sterile, very clean before they are shot.
Okay, so basically we take extra care to not to take microorganisms to space to contaminate other planets
Yeah,
where we visit. Yeah,
that's it.
that makes sense. And you said there are several screenings that are performed before a particular spacecraft is even allowed to go to the payload, right?
Yeah.
Okay, so
Mm-hmm.
so viewers, there is no need to panic about contaminating other exoplanets or other planets through our space explorations. So, ma'am, coming to the last question of the session, I would like to ask you, uh, what are your plans with your future aspirations in your career? Like, what other fields of research that you would like to get into?
Okay. So initially, this is actually my story. As I mentioned before, I have biochemistry background. For my degree, I had BSc in biochemistry. For my master's as well, BSc biochemistry, but tilting to membrane biochemistry and biotechnology. Then for my PhD, I had that as well in space biochemistry, because the kind of research that I did is using simulated microgravity environment to grow plants, and then at the end of the day, deducing some biochemical characterization on those plant samples, like the roots, the shoots, and others. But before then, I was employed in the Space Agency of Nigeria just as a biochemist. So it was getting there where I am part of the, should I say, forerunner of the space life sciences in the Nigerian Space Agency. So getting there, I was like, okay, I'm a biochemist. So how do what am I expected to do? And then I began to research, and my curiosity, was as well increased. So, and then I liked where I got myself and what I'm actually doing. So there's been so many experiments I've actually carried out using the simulated microgravity environments, specifically clinostats. You know, I've grown diverse plants, economic essential plants, you know, and I've deduced several results on them as well. Used some grown like input some small animals as well in such environments to see the effects, like on lizards, to see the effects on the cardiovascular system as well. So birds, I'm still very curious. I want to access the real microgravity environment, you know, to take those samples to the real environment, like going to the space station, you know, doing the experiment, conducting the experiments myself, not giving someone to do it for me, you know, getting them myself, performing the experiment. So it's still possible for me to be that astronaut that will conduct that experiment myself. So that is one of the interests, you know. But more and more importantly, the benefits of those experiments, the socio-economic benefits of those experiments that are actually conducted, bringing them to life, like those plants. There has been diverse benefits in the biochemistry that are grown under gravity environments. If I may expand further, like that's antioxidants, the benefits, you know, as humans, as animals especially, we breathe in oxygen, and this oxygen makes us to be alive, you know, and then without the oxygen, life is gone at all, the animals. But this oxygen we are using to breathe, it is also detrimental to our health. So it is causing some havoc on the cells of our bodies. And then God actually built it inside of us, you know, some countermeasures, but are not sufficient. Therefore, we need to get some of these countermeasures called antioxidants, you know, from her foods. So under microgravity environment, there has been an increase of antioxidants of plants that are grown under microgravity than those that are grown under normal earth gravity. So that is just one of those benefits. So performing research, you know, that have such socio-economic benefits is of great importance.
Yeah, it's a kind of an interesting thing that you mentioned, that yeah, the oxygen, the very oxygen that we breathe is also in some way detrimental to our health, and we have to take in antioxidants to counter that. That's interesting. I didn't know that. So
Wow.
with that, we come to the end of our session, and a very, very, very thank you to you know, ma'am, and for attending this session, and to our subscribers and listeners, do like, share, and subscribe, and do follow us on Instagram, and we hopefully would be able to bring up more and more interesting people from various fields in our podcast. And thank you, ma'am. Thank you very much for joining this session once again. And with that, we
Thank you.
end today's session.
Thank
Okay.
you.